Hi everyone. It's hard to be on this stage after this amazing keynote. So I hope to keep the level up. So thanks a lot, Julia. And like she gave some introduction to what I'm going to talk here, which is not live coding a compiler, but we live code a compiler. But my goal here is to, overcome this emotional hurdle about compilers, which kind of feels scary sometimes. But anyways, so it's good that this early morning. So you're all fresh, and we can live code a compiler together. I'm Fabrizio, and this is my Twitter handle, so you can send complaints, comments, questions, hugs. I probably won't have time to answer questions, so you can send them there. What happened? Right. Oh, no. Yes. So as Boshidar said, I come originally from the beautiful island of Sardinia. Well, yes, and yep. And I moved. Nowadays I live in the up north in the beautiful Finland, where we have an abundance of three amazing things: forest, snow, and Clojure. I'm also well known for trying to talk about food in every talk I give. I had to promise I wouldn't do this today, so I won't talk about food, but they didn't forbid me from showing food. So this is a picture from my last talk in Helsinki, where I talked about Dhall, which is a great Indian dish, but also happens to be a new configuration language that I work on. And this is relevant because today we're going to talk about compilers. And Dhall is the reason why I got into compilers in the last 2 years or so. So a quick poll. Who thinks here that compilers are kind of scary or magic? Right? Right? So yeah, like half of the room. I used to think so, too. Think about this. At university, I took a course about compilers, and I just dropped out halfway through because it was like, no, I cannot do this in my life. So I feel like I'm truly a convert here, and I hope to show you that compilers are like normal programs, like there are data pipelines as you code every day, as I code every day. Yeah, they're a normal program. So I hope to convert you too. So here's a meme. Let's define a compiler. Yeah, this definition doesn't sound right. This is about the right one, but this definition kind of reads like a mouthful. So I usually try to explain compilers to people as translators. Compilers are programs that translate from human languages as we write programs and as we encode programs to machine languages, so something that the machine can run. So it turns out, in order to make a compiler, we also have to have a language that we have to go through. There are many languages available, so we could pick one and go with that. But today we're going to make our own language, and just to show that there's no special magic. So here's the rough to-do list on how to make a language. No worries if you're not familiar with all of this. We'll go through all of this today. So at first, we have to kind of read up on some computer science theory and like what's a computational model and stuff like that. Today, we'll pick Lambda calculus as a computational model. And then we have to come up with a syntax. That's the hardest part. Then we have to define some data structure that we will encode our syntax in. Then if we want a type checker, yeah, we can pick a type checker. We don't have to make one. We just pick one. And then we have to define how we're going to execute this language and where we're going to run it, like on the Clojure machine or on assembly or whatever. So let's make a language. And I call this language Heartlang in honor of this great conference. And here we can refine a bit more the previous to-do list. And let's define the Heartlang compiler phases. So we have some source in some syntax that we will define. Then we parse this source. What does parsing mean? Parsing is the action of taking some string or something that you type down and transforming that into AST, which means abstract syntax tree, which is just the data structure that represents your syntax in our program. It's going to be a Clojure map in our case. Then after we have this AST, we will make a type checker. And a type checker is a program. You can think of it as a friend of yours that has some rules written down, and then you go to them, and then you're like, OK, is this program good? And your friend will say, yes. or no, this is not a good program. And we'll tell you the reasons why. So it's a yes/no machine, right? Then after we have some valid AST, so your friend has said, yes, this is good, then we can normalize our program, which is some lingo for execution. We can execute our program. And then after we have this evaluated form of our AST, remember that here on the right you can see that the program is always encoded as AST inside the program. So after this phase, we can output some assembly, as compilers do, or we can output some Clojure. But in our case, we're going to pretty print the result back to heartlang source. Make sense so far? Right. So you see, this is a toy compiler and has some phases, but this is not really far from production compilers and like real-world compilers. Like here you can see the ClojureScript compiler has basically the same phases, except it's missing a type checker. And the Rust compiler has basically the same phases, but it has multiple phases of type checking. So this is kind of close to the real world. So it has a surf emoji, so I remember to drink, and you can breathe. So let's start actually doing things. So this was a high-level perspective. Now let's dive into this. So what's Lambda calculus? Who's familiar here with Lambda calculus? Right, half of the room. So for the rest of the room, so Lambda calculus is a logic model that models computations. It was invented roughly 100 years ago, like roughly a century ago by Alonzo Church. And you might know the equivalent model, which is the Turing machine. I find Lambda calculus simpler to reason about and to model languages on. So Lambda calculus is composed by a syntax, so how we define expressions, and some reduction rules that allow us to manipulate these expressions and make something meaningful with them. You can see that the syntax is composed by a few pieces. So this E is an expression, and an expression could be a variable, or it could be an abstraction over an expression, which we know it's a function definition, basically. Or we could have an application, which is function application. So since this might look unfamiliar, let's translate this to Clojure syntax. This looks familiar, right? So we have defined the syntax. Let's see some reduction rules. Today we'll see only one, which is very important, but there are many other reduction rules that allow us to manipulate Lambda calculus programs. And the beta reduction rule, it's basically function application. So it says something like, OK, if we have a lambda on the left side and a value on the right side, then we can take this value and replace it in the body of the lambda for every occurrence of the lambda variable. Does it make sense? Cool. And then we can throw away everything and just return the body of the lambda with the stuff substituted in. So this is beta reduction. It's just function application as we know it. So we can define basically all programming languages on top of Lambda calculus. In fact, you can see that Clojure is just a big extension of this, right? Like we define a whole bunch more rules, and then we get Clojure. Or we change the syntax, and we get Python, or whatever. But today, I'm going to talk about a smaller extension of this Lambda calculus, which is called simply typed Lambda calculus. And this is because I promised to live code a type checker, so here we go. And it's a small extension. You see that we add constants that C there, and then we add a type annotation on the function argument, so that X is going to have type T. Let's translate this to Clojure syntax. This is not Clojure anymore, because we have this funny type annotation there. And that means that we have the X argument of the lambda, and that's going to have type T. So this is heartlang syntax already. And we have constants. For example, numbers are constants. And we have natural, which is a type. So let's see about how we parse this into AST. So it's demo time. So here we can see some syntax. Can you see this clearly in the back? Amazing. So So we can have naturals, and we can have symbols, and we can have types. Let's see if I can use this. Yes. And so this type name, and this is a function type. So this arrow here is not the usual threading macro you're used to. It means that this is a type of a function from natural to natural. And then we have lambdas, which have type annotation, as we saw. Then we have function application, and then we're going to define addition just to exercise the numbers in the type system. So if I wouldn't have to code this whole thing from scratch, it would take 2 hours if I have to speak also in the meanwhile. But so here's the parser. Just wrote it down. We're just evaluating this. And yeah, so we're just going to show it. Cool. So let's just test the parsing here. So we can see that if we parse a 42, then we get a Clojure map with an OP, which stands for operation. So this is a natural, and contains some data, which in this case is a number. If we parse a variable, then we get that this is a var, and it has symbol x. Does it make sense? Cool. And so on for types. So we see that this is a natural, which is a special thing. Then here we have lambdas. So let me make this larger. Yeah. So we have a lambda with argument x, and then we have the type here, and then we have the body here. So this is kind of nonsensical. This would not type check, and we will see later why. But for example, this is an addition. So we have a and b, which are the operands to the addition, and so on and so on. So we know now how to translate syntax as we type it down to AST, which is the data structures in our programs. So I'm going to define a pretty printing function so that if we parse something, so we get AST, but if we parse and pretty print, then we get the same source back. Make sense? So that's it. Next, now that we know how to translate the syntax into AST, let's see how we type check this. So let's define the rules that this type checker is going to have to accept or reject our programs. And I could bore you with the mathematical syntax, whatever, with Greek letters and so on, but that's not fun. So it's funnier to talk about it with emojis and colors. So here's a box, which is going to be our type checking context. It means that we can open this box and look into the box and say, okay, what's the type of this? What's the color of this? And then the box will find things in the box. And as we encounter things like variables, we will put them in the box and say, okay, I found this has type this, or this has this color, I'm going to put it in the box. And that's a scroll, and that's our program. Feels kind of a scroll. And here are 2 colors just to show the different types. So we have 4 rules in simply typed lambda calculus. In more complex type systems, we're going to have more rules, but this is the simplest typed model that we could have. And this rule is about variables, and it goes something like this. So if I have an x in my scroll, so I have a variable x in my program, then I look into the box, and then I search for the color of this x. In this case, we have the x in the box, so we find, okay, this x has color yellow, which means this x has type something. The second rule is about constants. So in this case, we don't even have to have something in the program. We just look into the box and say, okay, 3 has color green, right? This is the most complex rule, and it's about lambdas. And it goes something like this. So if I have a box, and I put x of color yellow in the box, then I could find in the box some e of color green. If this is true, then it means that if I don't add x in the box, then I find a function from yellow to green. Make sense? Cool. The 4th rule is about function application, and it says that if in my box I could find an x of color yellow and a function from yellow to green, then it means that if I put this x into the function, I would get something of color green, right? Because I put the yellow thing in there, and then I get the green. So let's code this stuff. So we have to first define some facilities in order to represent our box in our program. And in this case, I'm just going to use a list. So whenever we encounter a new variable, I'm just going to attach to this list something like, OK, this variable has type this. And then whenever we need to search in the box, we're just going to look in the list. OK, can I find something called x? And so on and so on. So I'm just going to evaluate this, because it's super boring code. Right. And let's write the type checker. So, you know, we could have some invalid states. So we go to our friend, and we say, is this program good? And our friend says, no, we have to represent this inside the program. So we're just going to throw exceptions with super bad errors. But if you want, you can have nice errors in your type checker, right? So let's just evaluate all of these invalid conditions. Cool. And let's write down the rules. So we saw the first rule is about, so we look up in the box and search for the variable and get the color of it or the type of it. So we're just going to do that. So if we encounter a var, we're going to do an iflet, and we'll bind the type, and then we do a context lookup here inside the context, and then we'll take the data and symbol here. So we get the symbol of this, and put it in the context lookup, and we're going to look up for this symbol. If we find this, then we can just return the type. If we don't, then we throw an unbound error. So this means that the variable was not found in the box, and this is a problem. So let's evaluate this. It's fine. Let's go on now to the second rule, which is about constants. So, you know, we don't even need to have these things in our program. We just know their type or their color. So if we encounter a natural, then we can just say, OK, this has type natural. Easy. And if we encounter the natural type, then we can just say, OK, this is a type. All right, nothing really new here. Let's go on to the more complex rule. So let's look at it again. We have to add x in the box, and then we have to get out an e of color green. And if this is true, then it means that we have in the box some function from yellow to green. So we have to encode this. So here I do some destructuring to get out the symbol, the type, and the body of the lambda. And then the first thing we do is that we type check the type itself, because that needs to make sense. And then we create this new context with the x inside it. So we do a context insert in the context of the symbol with that type that we just type checked. So we know that this makes sense. Then we create the new the type of the body with the new context. So we type check the body with the new context. All right. So if all of this is fine, yes. Oh, thank you. This was great. So if this is fine, then we can return the type of this function. So we create this type. In literature, the type of functions is called pi for reasons. So let's just use that. So it's a pi. And then it's going to contain A with the type and B of the body type. And this means that we have a function that goes from the type that we define that our function has, because we annotated that, we literally wrote that down, to the body type, which we just calculated. So the last thing we have to do here is that we have to type check that this makes sense. And we'll see why in the next rule. So we do a type check of pi in the context. So if everything is fine here, we just return the function type. So we evaluate this, and it's fine. So here we have to type check the pi itself, which we just did here. So we need to be able to execute this operation. And we have to ensure here that the type annotations are going to be types. And because, for example, if I write something like this, parse function x of type 42 and returning x, this parses, but this wouldn't type check because it doesn't make sense. 42 is not a valid type. We cannot say that some x has type 42. It needs to be a type. So, for example, in this case, natural would be an OK. Oh, sorry. Natural would be an OK type. So we have to ensure that this is valid. So let's write down this. So with the structure here, the A and B, so the input and the output type of the function type. And then we do, the first thing we do is that we type check both the things. So we type check A in the context, and then we type check B in the context. So we do this, and then now we have to say something like, OK, if both of these types are type, then everything is fine because the input and the output type are types. So it's good to go. So let's write this down. If and and equals. So if the operation of the type check of the type of A is type, and the same but for B, type B prime, then we can say, all right, this is indeed a function type. So it's a type. If not, then we have to say, this is not a good function type. So we throw an invalid pi. Cool. That's good. Now for the last rule, this is easier. We have to look in the box and find x of color yellow and a function f of from yellow to green. And then if that's valid, then we can say, OK, we have a green there. So let's write this down. And so what we do here is that, well, as usual, we type check the two things here. So we type check the f in the context, and then we type check the a in the context. And here we have to check two things. So the first thing is that the function that we're applying is actually a function, right? So we need to check that the operation, of the type of this function is equal to pi. So we need to check that this function has a function type. If this is true, then, oh, sorry. I think I'm missing something. No, this is right. So if this is true, then we can continue our execution. If this is not, then we have to say that this is not good, and we have to, and this is a wrong function type. Cool? Now we know that the function that we're applying is a pi. So the type of the function that we are applying is a pi. So we have an input type and an output type. Then we have to check that the input type is the same of the type of the variable that of the value that we're applying to the function, right? Because the colors must match. Yellow must be yellow. So we do this check. So we check that equal a type is the same of function type and then the input type of the function. So if this is fine, then we just return the output type the green, right, of this thing. So f-type data b. If this is not true, so if we're trying to apply a function from yellow to green to a red, then we have to say, you know, these types don't match. So we throw a type up mismatch. And here we add some information, f-type, a-type. So in reality, you will have nice errors and so on and so on. But here, we're cutting corners here. So we did it. That's it. That's a type checker. Here, I wrote down some additional type checking rule for the addition. And in here, we're just checking that if we have an addition, then we have two operands. We're summing two things. And then we have to check that the types of these two things are natural. If they are both natural, then we can actually perform the addition. And we can say, OK, the type of this addition is natural. If we don't have these two, then we say, OK, there's a type mismatch here. I cannot add a type and a natural. And that's it. So let's test this type checker. So here we define some like small function to take an expression and then parse it and then type check it. So let's just type check 42. And indeed, we get that 42 is a natural. That's fine, cool. And then here you can see that if we try to look up in the box for something that we don't have, so if we try to type check x alone, then we get an error that this is an unbound variable. This was not in the box. So that's it. The type checker might fail. Let's see what happens when we try to type check a function by itself. Then we get that this is a function, is a pi, from natural to natural. Let's type check some addition. Here you see that both members of the addition are natural, so the type of the addition itself is natural. Let's define some more complicated function and see the type of that. This is also a function from natural to natural. So let's just try to apply this function and see what's the resulting type. What do we expect here? It's natural, because if we apply a function from natural to a natural, we get a natural back. And indeed, this is true. We get a natural. The type of this is natural. So, but this is a functional language. We could also pass functions inside here. Now, I don't know what's the type of this. We just asked the type checker. This will return a natural eventually. That's cool. We have done a type checker. But we're not evaluating things here. We're just checking that their types match. We're not calculating the value of the program. So let's just do that. And that's the next phase. So we have a valid AST. So the program is valid. We have to type check that. We have to evaluate that. So I won't write that. Like, it would take 2 hours, right? So I'm just going to evaluate this. But let's look quickly. This is the beta normalization phase. So we find a lambda and a value, and then here we do the function application, and this is it. So you don't have to read this. All the code is open source anyways. I'll link you to that later. But let's evaluate this and try that our compiler actually works. So here I define a small function that parses, type checks, and then normalizes that, and then it pretty prints that. So if we execute 42 by itself, then we just get 42. If we evaluate this function, then we get some gibberish names, but in the end, it's actually just a function from natural to natural. But what if we apply this function? Then what do you expect we get here? 42, right? Let's see this. Yes, and we get a 42 here. Let's try the addition. Addition works. Let's try to add something. From a lambda to a number, and here we should get 43, and indeed we get that. And so on and so on and so on. And that's it. We just made a compiler. So we have done this. Here's some food for thought. So what we just did, we made up a language. We implemented a compiler for it, and it works. And I hope to have shown you that compilers are not magic. They are data pipelines. So we get data, we manipulate that, and we get some result at the end. Also, type checkers are not magic. They are a sequence of if and else, like AI. And the hard part, is done by researchers. So like people that actually works out the math. You don't need to learn the math in order to implement one. And if you do want to learn the math, the learning curve for learning the theory is not steep. It's long. It takes time. It's an amazing trip. I really recommend it. But it's not steep. You can do it. So you might be asking yourself, all right, but how is this useful in real life? I don't write compilers every day. Maybe I wish, but I don't know. But as Clojure programmers, we create DSLs all the time. We create rule engines. We create all sorts of programs that kind of are doing the work of the compiler without being compilers. So it is useful to know some programming language design and implementation. So for example, the language that we just made up is not Turing complete, which is a very interesting property. So it's useful. I find it useful to know this kind of stuff. Because, for example, if you're making a rule engine, you don't want that to be Turing complete, right? You don't want your user to be able to, like, just, DDoS your machine or whatever. And the final message that I would like to leave you today is please make your own programming language because we need better ones. Thank you.